start sending back data. We are now sending our high-speed data of about 4 16-megapixel images every 3 seconds to the ground. SDO is the first mission in the Living with a Star program. It's designed to study the sun and how the sun affects us here on the Earth. Most of these effects come from the magnetic field of the sun, and we're going to see today that that magnetic field is never the same twice. It's always changing. Today we will show some of the earliest data from SDO. We will see new things with each instrument. The first is the helioseismic and magnetic imager. HMI will measure the waves rippling across the surface of the sun and the strength and direction of the magnetic field at the surface of the sun. Using those waves, we can actually look inside the sun, and in fact, we can look all the way through the sun and see what's happening on the other side. It's a great thing that we've been using for a while, and HMI will allow us to do better. The next instrument is the Extreme Ultraviolet Variability Experiment, or EVE. That's built by the University of Colorado, and that measures the heartbeat of space weather, the extreme ultraviolet emissions of the sun. This data will tell us what the sun is doing to the upper parts of our atmosphere as it affects our radio communications and causes satellite drag to bring satellites down. Our first picture from EVE doesn't look anything like it should. It's a beautiful image of a CCD image of the spectrum where things that are red are bright and things that are blue aren't bright. But the cool thing about EVE is they found a little spot on the CCD, and in the lower right-hand corner, you can see a small image of the sun, and that's in very short wavelength X-rays. Our third instrument is the Atmospheric Imaging Assembly. That was built at the Lockheed Martin Solar Astrophysical Laboratory and will bring us extraordinary image of the sun's corona and chromosphere. AIA will record images of the full-disk EUV sun at a pace and with more channels than we have ever before achieved. This will allow us to zoom in on small regions and see far more detail in both time and space. Here we see an image from AIA at about 80,000 Kelvin. We have two more, and there is excessively hotter parts of the sun, up to about 2 million Kelvin. We have so many channels on AIA that we're actually having problems deciding on what false colors to use to represent these images. So I hope you understand our problem. The first movie I saw from AIA was taken the very day that they made the detectors cold and could take a good picture. And we're going to show that next. It's a little part of the sun, and we see what's called a prominence eruption coming off of the surface. Now, it's not a very long movie. We're going to loop it around a couple of times so you can see it. But I called in another solar physicist to look at this movie, and he laughed and said, well, that disproves another theorist's theory. So, of course, I went to the other theorist, and I said, well, what do you think about that? And he said, well, it may disprove that theory, but I have another theory that also explains this. So we're already learning new things from the images that we're seeing and from our instruments. But this is only the first view. And now I'm going to let Alan Teitel from the AIA instrument talk about even more of the images that they've been able to take since they started. Alan?
Thanks, Dean. Thank you for showing my movie. I wonder if we could have the first slide, please. Okay. This is not a cartoon. This is the real instrument. You can see the 4 AIA telescopes, and behind it, the SDO spacecraft. This is an effort of a number of years by many hundreds of people. And the fact that this all worked from the first moment that it was operated is just an astounding tribute to the people of our team and the people of NASA and the people who launched this rocket. So if we could have the next slide. The next movie, please. This is a composite picture. And here's the images that Dean has shown, but now with the million-degree sun overlaid in green on the 80,000-degree sun. What I'd like to show you next is an event called a coronal mass ejection. There's a large wave that travels across the sun. It originates from a little magnetic region, and if you watch the brightening region, this is what the sun looks like at a sequence of temperatures. So this is a 1,000,000-degree sun. This is 1,000,006. And you can see the wave travel across the sun and the sun darken behind it. And these images don't really do justice to the resolution of the telescopes and the detectors. So we're going to zoom in and look at these regions with a little more detail. So if we could zoom in, again, here's the magnetic field that's responsible for all of this. And here's the sun at 80,000 degrees. And you can barely see in this image the signature of the wave, but you can see the region of the upper atmosphere of the sun heating locally in this very small flare. Now here's the sun at 1,000,000 degrees, and these frames are taken once every 20 seconds. So you see this wavefront moving out slowly. Actually, it's moving out at about 500,000 miles an hour. And you can see very clearly the dimming. This dimming is caused because the wave is lifting off the material of the corona. Here it is at 1.6 million degrees. The wave comes across, and if you look to the lower right, you'll see this bright region dim, and the region around the flare itself dimming much more strongly. And here's a 10 million degree picture, and you can see how much brighter the flare itself is than the local surround. Okay, so why do we take all these different pictures at different temperatures? We want to see what the physical phenomena are that are associated with the flare and this ejection of material. And it's not a trivial ejection of material. What we've ejected here is amount of mass about the same as contained in the whole Mississippi River, and we've ejected it at a speed of about 1,000,000 miles an hour, and we've accelerated it to 1,000,000 miles an hour in about 30 seconds. And this CME actually is a halo CME, which impacts the Earth. So now what we're going to do is start to put these images together in color, and so the images will go from blue to red, from cool to hot. Well, where in the first images, we're looking at 80,000 to 1,000,000. And this is another filament ejection that was associated with the wave. And now here's the sun captured in color from 1,000,000 to 2,000,000 degrees. And as the wave propagates across the sun, you can see the colors change. And that shows how the gases are heating. Now here's the blow up of the region. And as the wave front goes out, the colors change, and that tells us how rapidly the gas is heating. And now here's a sequence from 2 million to 6.3 million. And you can see the red and white regions. These are regions that are very hot. And as the flare goes off, if you watch the green lobe in front, this 1.5 million degree gas, and the red wave, as this flare goes off, we're driving that gas to 6 to 10 million degrees. And from this, we can begin for the first time to decode how this energy is released into the outer atmosphere. And because we all live in the outer atmosphere, how it impacts us. Phil, why don't you tell us how the magnetic field runs all this?
Right. So all of the images that you've seen from AIA and the data you'll see from Eve shortly come in the extreme ultraviolet. They're invisible. They come from high in the corona, or low in the corona, but in the corona, above the surface. All of the magnetic fields that structure what's happening up there